Okay, the next speaker is getting set up. So we're going to have a talk from Peihan Miao, and it'll be on Updatable PSI. And any minute now, we'll be able to see her title slide and verify that the title is, in fact, Updatable PSI. She's not updated it since it appeared in the schedule. All right, here's Peihan.
Thanks, Mike, for the introduction, and thanks everyone for staying for yet another PSI talk. Promise this is the last one. So I'm going to talk about updatable private set intersection. So I suppose by now you're familiar with this notion of PSI, where we have two parties, Alice and Bob, each have a private set of elements, and they want to jointly learn the intersection and nothing more. So although the functionality is very simple, it actually has found a lot of applications actually deployed in practice. For example, password breach detection deployed by Google Chrome, also iOS keychain, Firefox, Microsoft Edge, and so on. And also by Signal for private contact discovery, by JP Morgan, thanks to Antigone, for privacy-preserving inventory matching, and also by Google for online advertising measurement. And I just wanted to say a little bit more about this application, because it's relevant to us. So in this application, the two parties are an ad platform, let's say Google, and an advertiser, let's say State Farm. Google has a list of users who have seen ads on Google about State Farm, and State Farm has a set of customers who purchased insurance from State Farm. And the intersection of the two sets are exactly the users who have seen ads and then end up making a purchase. So this is what we call ads conversion. And this is a perfect application for PSI, and it's actually deployed in practice using PSI. Very, very cool. But if you look at what's happening in reality is that they're actually running PSI on very large sets, and they're running PSI on a regular basis, maybe on a daily basis or weekly basis. And from day to day, from week to week, they're only making small changes to these data sets. And more generally, it's not just in this application. In many of the other applications that I mentioned, sets are evolving over time, and people are regularly running PSI on these evolving sets. So this leads us to this natural question whether we can achieve some sort of updatable PSI, where parties regularly run PSI on updated sets. And our goal here is to make both computation and communication costs of every PSI to only grow with the small updates rather than the entire sets. And if you look at the PSI literature, there has been tons of work, all the way starting with the DP-Hellman-based PSI to the state-of-the-art vector OLE-based PSI, which I will talk more about later. But if you look at the existing frameworks and approaches, both the computation and communication have to grow with the entire sets. Basically, you have to run everything from scratch. It doesn't support any updatability. Okay? And this motivates our initial work to formalize this notion of updatable PSI, and also in our follow-up work, we gave updatable PSI protocols where computation and communication only grow with the small updates rather than the large sets. And I also wanted to briefly mention, maybe towards the end of the talk, our ongoing work that try to minimize the public key operations in these constructions. This is a joint work with Mike and our students, Junxing, Xingyi, and Jifeng, who are also in the audience. All right, so before talking about our results, let's first formalize the problem. Okay, so Alice and Bob each have a private set, and they run a PSI protocol to learn the intersection. And then on every new PSI execution, they're gonna receive some updates, elements to be added or elements to be deleted from their existing sets, which are significantly smaller than their existing sets. And they want to run another, so this is the new set, and they want to run another protocol to learn the new intersection. And again, our goal is to make computation and communication only grow with the updates. Okay. And here is our initial results, where we show 3 different protocols, all in the semi-honest model. The first 2 achieve addition only, where you can only add new elements to the existing sets. The first one achieved 2-sided output, where both parties will receive the output. And the second one is 1-sided output, where only one party receives the output. And in the semi-honest setting, the 1-sided implies 2-sided, because the party who received the output can just send it to the other party. So the first protocol achieved both computation and communication of order n, small n, which is the size of the updates. And surprisingly, if you want to achieve 1-sided output, it's a little bit more expensive. There is a log factor here, log capital N. N is the size of the entire set. And it's amortized over many runs. And we had another protocol with weak deletion, where we kind of keep a sliding window of the last T updates. All right. But there are a few limitations in our initial work. First, it only achieves the playing PSI functionality, where parties will learn intersection in the clear, like all the elements in the intersection. But in reality, people might want to achieve more advanced, more fine-grained functionalities. For example, in this application, the parties are actually prohibited from learning the actual intersection. Instead, they're only allowed to learn aggregate statistics about the intersection. For example, cardinality. Size of the intersection is one example. The other example is that maybe one party has associated values for all these elements, and they're allowed to learn the aggregate sum of all these associated values in the intersection. And more generally, there's this notion called the circuit PSI, where they learn secret shares of the elements in the intersection, so that after that they can run like generic UPSI on top of it. Another limitation is that we only support addition only updatable PSI, where in reality parties may want to arbitrarily add or delete elements. Another was for 1-sided addition-only setting, we can only achieve amortized complexity, and the worst case is still large, which means that on some days it's like as large as the entire set. And we fix all these issues in our follow-up work, where we can achieve addition-only, playing PSI, or cardinality, or sum, or circuit PSI with 1-sided output, where both computation and communication complexity is order n log n, and it's worst-case complexity. And we can also support arbitrary addition and deletion with another log factor. But if you look at all these constructions and consider the concrete efficiency or the computational assumptions, they actually all heavily rely on public key operations. But if you look at the state-of-the-art PSI protocols, it's based on vector LOE, and it's extremely efficient. Only a few public key operations, and all the rest are symmetric key. So in our ongoing work, we kind of resolve this issue. Like if you look at the assumptions, the prior work all like based on heavy public key assumptions. But in our work, joint work with Mike and our students, we can base the updatable PSI on VO in the random oracle model, which I will talk more later. I just wanted to mention that this is a subset of our results, and I'll talk more why that's just a subset. Okay, so here's the plan for the rest of the talk. I'm gonna focus on addition-only setting, and I'm gonna first show a 2-sided protocol as a warm-up, and then 1-sided output protocol, and then in the end, I would conclude with the VO-based protocol, how to minimize the public key operations. Okay, any questions so far?
Yeah, can you go back to your previous slide?
Yeah.
You have capital N in the end, like the big set, a small in the update, and where is the sender or receiver set?
Oh, we assume both parties have equal set size. And it's a very interesting question if you can extend to asymmetric PSI settings.
Yeah, then I have a follow-up question.
Yeah.
So can I run the PSI, because now I have small set, right? And I
Yeah.
have a couple big set. Can I
Yeah.
run the unbalanced PSI to do updatable PSI?
Yeah, we only focus on the balanced setting. And I will mention in the open problem, it's a very interesting open question whether you can extend unbalanced PSI to the updatable setting as well. Yeah, good question. All right, cool. So, okay, so if you know a little bit about PSI, the first thing that you might want to try is the Diffie-Hellman-based PSI, because it naturally has a kind of a streaming feature, and we will see why. So in the Diffie-Hellman-based PSI, you assume a hash function that takes arbitrary input and output a random group element where DDH holds. So in this protocol, each party, Alice and Bob, will randomly sample an integer from ZQ. It's kind of the secret exponent in the group. And then Alice will hash all her elements raised to the power Ka and send to Bob. I will denote this as h of x raised to the power Ka. And then Bob is going to raise all these elements to the power Kb. You get this set, and then also hash all his elements to the raised to the power Kb, and then send it back to Alice, and then, yes?
Sorry to interrupt in the middle, but it's something I don't understand.
Yes.
If, let's say, what they're looking at is the size of the intersection, and then Alice has some new elements and Bob has some new elements,
Yes.
and then she knows that the intersection is grown by 3.
Yes.
So she knows that out of these new elements, there are 3 that are intersection. What security guarantees are you offering?
So if you're considering cardinality, then after the update, Alice learns that there are 3 more elements in the intersection, which could come from her new elements, or it could come from her old elements, but added on Bob's side. So it could be her old elements, but Bob's new
But
elements.
that is some information.
Yeah, it
She
is
did
the
that before,
like.
so-
Yeah, it could be the yeah. So the only thing the thing that Alice learns is that the size of the intersection grows by 3. It could come from the old set, could come from the new set. Yeah, does that answer?
Okay.
So does that relate to your symmetric comment about why the problem needs to be defined balanced?
No, it's more because of the techniques that we use. Is
If
more.
one side set doesn't grow, then you do actually learn.
Oh, yeah, that is true. But the comment was more like if Alice and Bob have very unbalanced sets, even if they, yeah. But yeah.
Yeah, so I think that's why, come back to my question before,
Yeah.
like if the receiver don't grow, but the sender grow,
Yeah.
then you can use unbalanced set PSI, right?
Like all these protocols still work in the unbalanced setting. It's just that it doesn't help with complexity.
No,
Like the
complexity will be
complexity-
n and log n, like
Small-
unbalanced PSI still, like right now unbalanced PSI have n log n, and just n log capital N,
Ah,
and it match with the
I see,
complexity
I
that
see.
you have in your table.
I see. Okay. Let's talk offline. Yeah, okay, yeah. Sorry, let me continue with this. Any other questions before? Okay, cool. So here, then, okay, Bob is always where are we? Yeah, here. So Alice, Bob computes h of yi raised to the power kb and send to Alice, and then Alice will raise all these elements to the power ka. So if there is an element in the intersection, then it's gonna be both here and here, h of xi raised to the power kb, and h of like yj raised to the kb ka. So it's in the intersection, and then Alice can identify the intersection. So if you look at this protocol, it's actually like very updatable. Right? So if Bob has a new set of elements, he can just compute h of y these new elements raised to the power kb, and then Alice raised to the power ka, and then learn the intersection. Okay, so it seems already updatable. Now this is the first attempt where when both parties receive some new elements, they're just gonna continue running the Diffie-Hellman-based PSI, and then just learn the new intersection. Okay, correctness is fine. But if you take a look at the protocol for a second, it actually reveals more information than what Alice is supposed to learn, right? Yeah, exactly. Yeah, exactly. So besides the old intersection and the new intersection, Alice also learns the cross terms. Her old set intersect with Bob's new set, her old set intersect with Bob's old set, her new set intersect with Bob's new set, right? All the combinations she can learn. So this doesn't work. Now let's take a step back and think about what can be revealed to Alice in the ideal functionality. From the old set, she can learn the old intersection. And after the new elements added, she can learn the new intersection. And from these two sets, here is what she can learn. She's allowed to learn, which consists of two sets. One is her old set intersect with Bob's new elements. The other is her new elements intersect with Bob's entire new set. Okay? So if you look at the Diffie-Hellman-based PSI, the first set can be learned by the streaming feature. The question is how to learn the second set. And the second set is the intersection between a small set and a large set. So how can we do this asymmetric PSI with like little communication and computation? So if we're in a two-sided output setting where both parties learn the output, then the same thing happens on Bob's side. And similarly, Bob can learn this set. And the question is how to learn this set. Like, what does it gain us? So if you look at this set for a little second, it can actually be rewritten like this, where you can replace this large set Y by a smaller set. Because whatever in the intersection must be in this smaller set as well, which Bob can learn. So now we reduce to another PSI protocol where both sets are small. And we know how to do that. Okay, that concludes the two-sided output UPSI. But if you look at this protocol, it heavily relies on the fact that both parties learn the output. If only one party learns the output, this protocol doesn't work. Okay, so how can we do one-sided output? In one-sided output, okay, Alice can still learn this. The question is how to do this. Okay, and we're going to do this from what we call oblivious data structure, where at a high level, it works as follows. So Bob has a large set, and he's going to store this set in a somehow randomly shuffled manner and also encrypted form on Alice's side. And then, when Alice has a new element X, she wants to test whether X belongs to this encrypted database. But instead of comparing X with every single element, it suffices for her to just compare with a subset of these elements, let's say log n of them. Okay, using this oblivious data structure, which I will talk about in a minute. But let's say you can do this. Then all that you need to do is to compare X with a small number of encrypted elements. And this can be done easily using 2 out of 2 threshold additively homomorphic encryption, where the public key is known to both parties, and the secret key is kind of secret shared between the two parties. Each party only has a partial secret key. And these elements are encrypted under the public key. And then, so to test whether X belongs to this set, Alice can simply homomorphically compute encryption of X minus Yj for each Yj. So if X is equal to any Yj, then it's going to be an encryption of 0. Otherwise, it's encryption of non-zero. And then Bob is going to randomly sample some scalar to homomorphically multiply every encryption by a random scalar, and then partially decrypt using his partial secret key, and then randomly shuffle them. So what ends up happening is that if any of these match, it's going to be an encryption of 0. Otherwise, it's going to be an encryption of a random element. And then Alice can fully decrypt and see if any of these encryptions are 0. And then we're done with the comparison with encrypted values. Now, the only remaining question is how to construct this oblivious data structure that allows Bob to update the encrypted database in an oblivious way, but still allow Alice to query it in an oblivious way. This seems to be exactly what ORAM achieves, except the caveat that In ORAM, it's kind of the same party who make the updates and also later make queries. But here, it's one party, Bob, who makes the updates, but the other party, Alice, makes the queries. Okay? But our construction is actually inspired by the past ORAM construction. It's a tree-based construction, so our data structure is organized in a binary tree with depth log n. And throughout the entire protocol, we're going to keep the invariant that each element yi is always stored in the root-to-leaf path computed by h of yi for a public hash function, or in the stash, but you can ignore the stash for now. For example, for y15, let's say h of y15 is this root-to-leaf path, then throughout the entire protocol, y15 must be stored along this path, either here or here or here or here, somewhere. Okay? If we have this guarantee, then it's very easy for Alice to query for element x, because she can just simply compute h of x to identify a root-to-leaf path, and if x is in the database, then it must be somewhere here. Now the remaining question is, how can Bob add a new element to the database? So for example, to add a new element, y36, he's going to first put it in the root of the tree, and then he's going to pick a completely random path. If you're familiar with path ORAM, this is the eviction path. Completely random path. And then he's going to consider all these elements and push the elements down the path as much as possible. For example, this is y15. Let's say y15, h of y15 is this path. Then we can push it down along the random path to here. For y36, let's say y36 corresponds to this path. Then we can push it down here. And we're going to push all the elements down as much as possible along the random path, and then reorganize everything, and then we're done. Because this is a completely random path, so the access pattern is oblivious. And then we're done with the construction. In terms of performance, this is our addition-only UPSI cardinality sum and circuit PSI compared with the state-of-the-art PSI protocols. And as you can see, the communication really outperformed the prior work, because this is a state-of-the-art Vo-based PSI running from scratch. So obviously communication is better because we're n log n, but previously, these protocols are order n. But in terms of running time, we can only outperform when the updates are significantly smaller than the size of the entire sets. And the reason is because these PSI protocols are too fast. They're way too fast. Thanks to many people in this room who work on PSI, and Vo, who made everything extremely fast, very hard to beat. The reason is that they only require a little bit public key operations, and all the rest is symmetric key, like AES hash and extremely fast. But in our protocols, every operation is public key. So this motivated our work on making Vo-based PSI protocols also updatable, which I'm going to briefly talk about in the next, how much time do I have? 6. Okay, 5 minutes is enough. All right, cool. Before talking about our techniques, I want to give you a high-level overview for those of you who are not familiar with Vo-based PSI, how the Vo-based PSI work. So the construction is based on another building block called batched OPRF, which is a special secure UPC protocol where Alice has no input and Bob has a bunch of elements as input, which is his elements in the set. And from the protocol, Alice will learn PRF key k, a random PRF key k, and Bob will learn the PRF evaluated on all his elements. And then, since Alice learns the key k, she can evaluate the PRF on all her elements and send all the PRF values to Bob. And if an element is in the intersection, then it will appear both here and here, from which Bob can derive the intersection. Okay, so now the question is, how can we build this batched OPRF? We're going to build it from Vo, and another a data structure called oblivious key value stores, or OKVS, which you briefly seen in Jasper's talk, but I'm gonna briefly recap. So it's a data structure where Bob will prepare a bunch of key value pairs, which is in the form of yi and h of yi. This is a key, this is a value, and then he can somehow encode this into this OKVS data structure. If you're not familiar with the data structure, you can think of this as a polynomial. Okay, so this is just a simple polynomial interpolation where if you evaluate this polynomial on yi, it will give you h of yi. Okay, that's it. And then the two parties are going to run a vol protocol where Alice is going to input a random scalar delta. Bob is going to input this OKVS or polynomial or vector. You can think of a polynomial as a vector of all its coefficients, right? And then from the vol correlation, from the vol protocol, they're going to learn a secret share of this delta times p. This is not slightly different from the standard way of defining vol, where Bob actually learns like a random p, but you can get this version in a straightforward way as well. Okay, and then Alice is going to define her PRF key k as delta and a, and the PRF like this. There's some argument of why that is PRF and why Bob can evaluate it on his elements, which I'm going to skip. Okay, but this is the high-level idea of the protocol. Now, if you look at the protocol, if we can achieve some sort of updatability of the OKVS, then hopefully we can get updatable batched OPRF and then hopefully updatable PSI. What do I mean by that? So this is the initial set, and you encode into OKVS. Now Bob has some new elements. If you can also update this OKVS data structure by adding a sparse vector to it. By sparse, I mean that there is only a small number of non-zero entries in this vector. If you can do that, then the only thing that you need to do is to update this vol correlation by adding a small, like sparse vector here. And this can be done by running another vol protocol on this sparse vector. As long as this is sparse, you can do it efficiently with like low communication. And then Alice can update the key and so on. Yeah. Why are you?
Yeah, it's just a linear map.
Yeah, it doesn't have to be a polynomial. There are other constructions of OKVS and so on. It doesn't have to, yeah. I'm just using polynomial as an example. Okay, so now the only remaining question is whether it's possible to achieve updatable OKVS. And we looked into the literature of OKVS constructions, and none of them are very updatable, unfortunately. So what we ended up doing is that we revisited the construction from OKVS, and turns out we can actually relax some of the properties from OKVS that's needed for PSI, which I don't have time to go into details. But after relaxation, we actually give some updatable, like relaxed OKVS constructions with different trade-offs in terms of computation and communication. And one of the factors that contribute to the trade-off is whether the non-zero entries in this sparse vector is oblivious or not. Namely, whether you can reveal these non-zero locations to Alice. If you can, if it's safe to reveal, if it's oblivious, then you only need to run vol on these non-zero entries. But if it's not, then you need to hide the non-zero entries in this vol correlation, which is still doable. One last thing that I wanted to briefly mention is that this oblivious data structure that I talked about earlier actually has a very subtle security issue with adaptively chosen inputs, which only realized recently when working with Mike. So the issue is that for the adversary, after seeing the transcript, after seeing the current view, if they can adaptively choose the input for the next round, adaptively choose the updates for the next round, then there's a security issue, even with semi-honest security. And I have to admit, it was because I wasn't aware that semi-honest adversaries can also adaptively choose inputs in a reactive functionality. So the issue here is that if the adversary can adaptively choose inputs after seeing the transcript, after seeing the view, they can adaptively choose inputs that, all fall under this root to leaf path, so that some of the nodes would explode. So whether the nodes would explode or not would depend on the input, and which is not simulatable. So that's the issue. And we have some constructions that are still secure against adaptively chosen inputs, but not this construction. This is only secure against selective inputs. Okay, I'll conclude with open problems. So for this oblivious data structure, it will be very interesting to see if you can make it adaptively secure against adaptively chosen inputs. And we don't know how to support efficient deletion. Okay, and then for role-based PSI UPSI protocols, whether you can get rid of the log n overhead. This is very interesting because remember the sparse vector that I talked about? If it is oblivious, then there is a log factor. If it is not oblivious, then the vol construction has a log factor. So it's really unclear if this log n factor is really inherent or not. And then we only achieve the plain PSI functionality. It's interesting to see if it can extend to other functionalities. In our protocol, it achieves. Both parties have to keep this like kind of encrypted data structure, and it's very interesting to see if you can achieve sublinear storage even on one side. And all the protocols are semi-honest, whether you can achieve malicious security, and also whether you can extend updatable PSI to asymmetric sets. And that's it. Thank you. Happy to take any questions.
Any last questions for Peihan? Okay, well, if not, then thanks everyone for another successful day of the workshop. We will see you all at the usual time tomorrow. Are there any, there's no like organized stuff tonight, is there? Every night. You're on your own tonight. Sorry, we can't help with that. Good luck, yeah. I hope most of you survive for tomorrow morning.